So let's say that this is one of those receptors. And it's attached to a channel. So what that channel is, you can think of it as like a little doorway. So there's a channel, got a little door like that. Now, when insulin gets released by the body, it will come over and it will bind to this receptor on the cells. Now, what that does is, don't want to do that. What the insulin will then do is it will cause that channel to open. So what that means is then, just because of diffusion, and you've got loads of glucose out in the blood and not really much in the cells, all the glucose will go into the cells. And so what that means is you've got a whole load of glucose in the cells, and the amount in your blood drops. So you can get rid of all of these, and you're left with like a few. And so what's just happened there is this bit, this downward trend, where the blood glucose levels dropped because all of that glucose has now gone into the cells. So once it's in there, glucose is what is called osmotically active. So if you've done A-level, you probably know this. If you've done GCSE, you won't. So I'll just explain it quickly. But basically, what osmotically active means is that it will cause the movement of water. So osmosis is the movement of water from an area of high concentration of water to an area of low concentration of water. But in an area where you've got a high concentration of water, you automatically have a low concentration of solute. And in this case, osmotic reactant. I haven't heard the term before, but possibly. It sounds vaguely similar. Oh, osmotically active. So what that means is if you've got an area with a high concentration of water in it, you automatically will have a lower concentration of the stuff dissolved in the water, and vice versa. So where you've got a really high concentration of solute, the thing dissolved, you'll have a lower concentration of water. And so in terms of our cells, what we've got is we've got high concentration of solute, therefore low concentration of water. What that means is that the water is going to want to move from your blood into the cells and follow the glucose. But if it did that, then your cells would kind of just act like a water balloon, like they'd expand and they'd expand and they'd expand, but eventually they'd pop. So that's not very useful if we're trying to store glucose, if we're just going to end up popping, like bursting all the cells. So what our body does is it turns this glucose into something called glycogen. And glycogen is just kind of like, just think of it as like little boxes that you can store glucose in. And glycogen isn't osmotically active. So that means it won't cause this movement of water, which is what we want. So in terms of the function of insulin, just to sort of summarize all that, what we've got is it will cause glucose to move into the cells from the blood. And then once the glucose is in the cells, it will then turn to glycogen for storage. Okay, does that make sense so far? Any questions about that? Okay, I'll assume no. So that's getting down to like this point here after the release of insulin. Now, at that point, you can eat a meal or you can eat some food. But if you don't have any food around, your glucose, without any other mechanism, your glucose would just keep going downwards like that, which isn't ideal because glucose is what your whole body runs off. So if you don't have enough of it in your blood, you end up, your body doesn't fare very well. So it needs a way to anticipate the fact that it's not going to get any food and raise that blood glucose level up again if you don't eat anything. So that's where this hormone called glucagon comes in. And I do appreciate they are very badly named because they all sound the same. So what glucagon does is basically the exact opposite of what we've just said here. So instead of glucose going into the cell and turning into glycogen, glucagon causes the glycogen to turn into glucose and leave the cell. So I'll just write it. Causes glycogen into glucose and then out of the cell. And how I always used to remember that is it's glucagon, which means, all the glucose is gone from the cell. And that was my little silly way of trying to get my head around it. So that's how your body maintains sort of its blood glucose concentration. So with diabetes, what happens is it's one of two things that causes it. So diabetes is when you can't control your blood sugar level properly because you're not. How does glucagon trigger the? Okay, yeah. So similar thing. So just like insulin would bind to a receptor, and that would cause the channels to open and glucose to move in. Similarly, you'll have a receptor, and what that'll do is that will stimulate the glucagon to turn back into glucose and leave the cell. So pretty much everything in the body is done with some sort of receptor. Like if it's sending a message from one place to another, there'll be a receptor involved in there somewhere. So with insulin, I should probably say as well, insulin's produced in the pancreas. Okay, so with diabetes, what happens is you have issues with insulin, and that can be for one of two reasons. So you can either have one, you're not producing insulin, or two, you aren't responding to the insulin you're producing. And so it's kind of like on two ends of the system. So like, I suppose you could, like an analogy could be if you were trying to phone someone and give them some information, that information would not get across for one of two reasons. Either your phone isn't working, so you can't send the message in the first place, or you speak English and they speak French. So even though the message is getting across, they can't understand the message and act on it appropriately. Same thing goes here. You either don't produce the insulin, which means the receptor can't be triggered, and so the glucose just stays in your blood, or you're producing insulin, but the receptors aren't responding very well. And so that means that the glucose, again, stays in your blood, and that blood glucose level just keeps going up. And handily enough, these are the way that diabetes is classified. So it's type 1 and type 2. So going over type 1 first. So he said that insulin is produced in the pancreas, looks something like that. So in your pancreas, you have these little areas that are called, I'm going to draw them as little hexagons, even though they aren't actually hexagons. So just throughout, you've got these little areas, and what they're called is the islets of Langerhans. And basically, Mr. Langerhans was the guy that thought he could get famous off it. He was just the guy that found it. And within there, you've got two types. You have actually got three types of cell, but the one that we're going to consider is beta cells. These are the ones that produce insulin. Now, in type 1 diabetes, what happens is when the immune system is developing, it becomes sensitive to cells inside your body, which it's not supposed to do. But essentially, what that means is in type 1, the immune system will attack the beta cells. And if you attack the beta cells, then you don't get insulin being produced. And if you don't get insulin being produced, then it can't activate the receptors. So that's what happens in type 1 diabetes. And in type 1 diabetes, because you're not producing insulin in the first place, the only way to treat it is by giving type 1 diabetics insulin to inject themselves with. So they need to monitor their blood glucose and inject some insulin before meals. The actual regimes that they use can get quite complicated. So they have, actually I'm not going to go into it, but in essence, it just means that they need to inject insulin to get this whole thing to happen. Now, in type 2, what happens is you're producing your insulin, that's absolutely fine, but your body's not responding to it. And the reason it can do that is, just like before, I said that your body likes things happening in very certain ways and like certain amounts in specific ranges. Same goes for receptor activation. So if you activate the insulin receptor too much, your body starts thinking something a bit dodgy is going on. And so what it will do is it will take, if this is a cell and you've got a whole load of receptors on it, if you activate those receptors too much, what will happen is your body will say, okay, there's something wrong there. They shouldn't be that active. And so it will start, it's called basically internalizing those receptors. And for the purposes of this, basically what it means is those receptors are no longer there anymore. So whereas you started with like receptors that were functioning absolutely fine, you end up with less receptors. So what that means is even though you're producing insulin, it's got less receptors to act on. So it takes more insulin to produce a proper effect. And so that's why if you've got like a diet that's really high in sugary foods consistently, that's why you can develop type 2 diabetes, because those receptors are getting activated too much, so your body just gets rid of them. But what that also means is because you've still got some receptors left, you can kind of control type 2 diabetes with diet and with some medication. But you always start off with diet and how you do that is, so if we draw a little graph again. So whereas some foods have a whole load of sugar in them that will cause your blood glucose to spike like that, and that's when you need insulin, there are other foods, the healthy ones like brown pasta, brown bread, brown everything, wholemeal stuff that no one likes. What happens with the sugar that gets released from that is it gets released a lot more slowly. And so that means that as it's being released, you have time to work it off. And so you might not need to secrete as much insulin anyway. And the reason you can't let it just keep building up so that you release more and more insulin, because your pancreas can keep up, and it'll just keep releasing more insulin. But eventually it gets to a point where it can't, and the whole thing just gets absolutely knackered. And so that's why if you're a type 2 diabetic and you've got really poor control, then eventually your pancreas just sort of gives up and stops producing insulin altogether. And that's why type 2 diabetics then end up going on insulin as well, because their pancreas is no longer producing it anymore just because it's been overworked. So that is type 1 and type 2 diabetes. Any questions about that? That's kind of like a whistle-stop tour of them, but if there's anything that doesn't make sense. No? Okay. So then, the last thing is just to go on to autoimmunity a bit. So I said that type 1 diabetes is caused by autoimmunity. And the reason that happens is because when you're a baby in the womb and your immune system's developing, what it does is it takes the genetic material and it basically just shuffles it all up a whole load of different ways. And what that means is that you get immune cells with, okay, so actually, first of all, you should probably know that immune cells run on the fact that they've got a receptor on them. So let's make it look like that. Now, that immune cell will have a receptor of a very specific shape. And if it ever comes into contact with anything that fits that shape, that immune cell will become activated. And that will go tell your body that it needs to attack whatever has in your body has this shape. So, for example, bacteria, like, it'll look like that. But around the bacteria, it has a whole load of different molecules that have different shapes. And so when your body comes into contact with a bacteria and it detects that it's got that particular shape and your body knows that anything with that shape on it is bad, it will mount an immune response and it will cause that particular thing to be destroyed. It doesn't ask questions about what that thing is or why it has that shape. It's just if it has that shape, it gets destroyed. And when you're so in your body, you've got immune cells that can basically respond to every single shape in the world ever. So that means that in your immune system, you have immune cells that can respond to diseases that don't exist anymore, all the diseases that exist now, and any disease that will ever exist in the future, which is quite cool. And that's why for like coronavirus, even though it's something that's completely new and just developed, we can still mount an immune response. We can still become immune to it. If we didn't have the ability to respond to every possible molecule shape under the sun, then someone with coronavirus would just get it, and that would be the end of it. There'd be absolutely zero chance of them becoming immune. So that's how the immune system works. It's basically just this fancy, like, does this shape fit me? And if it does, then I'll attack it. But your body, all the cells in your body have specific little shapes on them as well. So I've drawn all the easy ones down. Okay. So like, if this is a cell in your body, maybe that'll have a hexagon on it. And with your immune system, when it's developing, it's actually really smart. What it'll do is it shuffles up all the genetic material so that you get all of these different possible receptor shapes that it can respond to. And as that's happening, the thymus, which is the gland that actually produces a lot of these immune cells, it will just randomly throw into the mix a shape that's found in your body. So in this case, the hexagon, or like found on your body cells. And if it detects anything responding to that whatsoever, it will kill off that immune cell because it knows that that immune cell is going to attack your body, which you don't want. But with autoimmune diseases, what happens is that goes wrong. And for some reason, like that cell will respond, but the thymus won't kill it off. And what that means is you get a whole load of cells going out into your body that can detect your body cells and will mount a response against it and basically tell your body that it's not supposed to be in there, even though it is. And as part of that, as part of the immune response, you produce antibodies. So what will happen if we go back to this cell? So this is called a T helper cell, which is just a type of immune cell that helps to mount a response. Once it detects its shape has been filled, it's got a link to another type of cell called a B cell. Now the B cell has the exact same type of receptor on it that the T helper cell did. And so when it detects that this T helper cell has become activated, the B cell will then activate itself and throw out loads of what are called antibodies. And so what antibodies are is they're just this little receptor, but they have this little alarm on the end, if you like a massive flashing light. And what will happen is if these receptors come across something in your body that fills that sort of that niche, if you like, this will go off. Now, once that goes off, all the immune cells that are anywhere near will come over and absolutely batter whatever's in there. They won't go oh, okay, this has become activated, but why has it become activated? They will just mindlessly go in and kill off whatever has activated it. So what that means is that when you get these T helper cells being produced that are responsive to cells in your own body, but the thymus doesn't kill them off, when it detects that they will respond to your cells that are in your body, then you get antibodies released to the cells in your body, and these are called autoantibodies. Sorry, I realise I'm saying body a lot here. So autoantibodies. Basically what that means is they're antibodies for yourself, so auto just means you. Now, in type 1 diabetes, the antibodies are very specific to these beta cells. So what will happen is they'll float around the blood. As soon as they get into the pancreas, they will attach to all the cells that have that beta cell receptor on it. And once they've attached, their little alarm goes off, and all the white blood cells from nearby will come over and destroy those cells. And so that's why people with type 1 diabetes end up with, get it, because they don't have any beta cells anymore, so they can't produce insulin. And that's all down to that immune response. I realise that's fairly complicated. So is there any questions about that? I've also gone quite quickly as well. No, I saw Johnny typing, but nothing's appeared. Oh, there we go. Yeah, cool. His videos are good. They have much better animation than I do. Like, they will be considerably better than my little stick of drawings. So yeah, definitely go watch that if you're interested. Cool. Well, then I will leave that there. Perfect. Thank you for coming. And remember to donate if the link's still up somewhere.